over the last couple of weeks, I've played around a bit with build systems or on-demand incremental computation engines. And I learned a few things along the way I thought might be interesting to share with you, some aha moments. And what I'm going to do today is I'll pretty much like walk you through an implementation of a monadic build system, and I'll implement that in TypeScript. I assume everybody is like somewhat familiar with that. And I also assume I don't need to sell you like two build systems. I would assume everybody here kind of like has an understanding why build systems are useful, and I don't need to sell you on that. Is that a correct assumption, or is there somebody who needs to be sold? Okay, I guess nobody needs to be sold.
It's correct. I don't need to be sold on it. It doesn't mean I'm going to use one though.
Okay, cool. Then let's dive in. So build systems are often used for programming language, like to build stuff written in programming languages, but you could do a lot of other things with it as well. And today I don't want to focus on all the programming language aspects of like that you would encounter when using a build system. So we have like a very, very simple toy programming language, and let me jump straight into my editor. Can everybody see that? Can everybody like distinguish the different colors?
Yeah, we can.
Okay, that's great. Should I make the font a bit bigger?
Yes, please.
Okay.
Perfect.
Cool. Okay, now I have enough space on my screen. So as I said, we have like a tiny toy programming language, and it's not really a programming language. There will be two sorts of files. I need to get focus here. Kind of like problem description. So there will be two sorts of files. There will be star.lst files, and they contain a list of other files. So like a star.lst file could look like foo.dat, comma, bar.dat. That's how like an LST file will look like. It's just like a list of files separated by commas. And then there are dot files, which are just a number, like 13. And running an LST file means going into all the listed files, getting the numbers, and adding them. That's a programming language. We can add a bunch of numbers, but it's very complicated because it's spread across files. And the interesting part is, as I said, the build system around this. So what we will do, before I go into how to implement the build system, I will show off the API I'm intending to implement. So there's already some file in the background, which has the API, but full of holes. And I'll show how to use this API to do this. So the first thing we need to do, the first thing we need to do is we would need to write a spec. And like build systems usually are concerned about have a computation graph. So we need to spec a graph. And let's do that later. And assuming we have this graph, what we want to do is we kind of want to tell the build system, this file contains this text, this file contains that text. That's kind of the things we can tell the build system. And then we can go and ask the build system, what's the value of this thing? So in our specific example, let's say, let's assume we have a graph for the spec we still have to write, and then we can do things like get set input, and we want to set the input. Now we want to set like file content. So we want to say the file contents of the main.list file are the ones I have above. So let's say it's this string. And then we want to set the input of another file, namely the foo.dat that is referenced, and that number is 13. And then we want to set another in like the other file contents of bar.dat, and that will be, I don't know, your favorite number 42. And once we've done that, what we want to do now is we want to ask the build system for a value. So for instance, we could ask for get the value for, and now we want the evaluate like a list file, and we want to evaluate the one called main.list, right? And we expect this one expected to print what is it, 55. Okay, so that's kind of like the API. And then you might go and say, oh, like one of your inputs has changed. So let's say bar file contents bar.dat is now 24. And then if we print the output again, we would expect to see 37, right? And what we don't expect when we do this, we don't expect like the main file to be repassed or foo.dat to be repassed. Those should be like, they are cached in this huge graph we have in memory, which is driven by the build system, right? And then there are also other things. Oh, I've got a lot of things wrong here. I mean, there are strings, not numbers. And then there are other things we want to achieve. For instance, if I set the input of bar.dat to, let's say, space 24 space, and then ask, what do we get? I expect like still the same number, but kind of like I expect the build system to stop after it has noticed, oh, the value hasn't changed, right? Like the file content has changed, but the value of parsing the file content hasn't changed. So we expect early cutoff here after we've noticed that 24 is 24. Okay, does all of this make sense so far? Okay, I see people nodding. I interpret that as yes. Cool. Okay, so that's like the way we want to use this build system, and now we need to spec it. And the way we're going to do this today is we're going to say there are file contents, and file contents are not really, there's like nothing computed. So they're an input rule, and we just say like the rule to compute them is null. So we always need to set them from the outside. And then there's another rule which parses a list file, parse list. And this rule gets two inputs. It will get a graph, like it will get access to the whole graph, but in read-only mode. So what we get is like a graph reader. And we also get access to, let's call it the file, which is just like the file which we want to parse, or the name of the file which we want to parse. And this whole thing will return a list of strings, because that's how we intend to interpret the contents of a file. And what we do then is, well, we get the contents of the file, and then we get them by asking the build system, what is the file content? So we ask, what are the file contents of the file we care about? And we know this is a string, and there's some type holes in our system, so we need to tell it explicitly that we're talking about strings here. you can make this you can make the API of this better, but I think that's not the interesting part for now. So, and once we have those contents, we say, well, contents, and we split them along the commas, and then we're done. So that's just a rule for parsing, right? Like usually this is like way more expensive, and we would try to avoid doing this whenever we can. Yeah, but like here it's cheap, but it's just meant to be a proxy. Okay, and then like similarly we have like parsing for .dat files, which takes again. Let me copy paste. So which takes again read access to the graph and the name of the file. We get the contents from the build system, and then we just turn them into a number. Oops. So we say we return a number, and here we do number parse int, and we take contents dot, and we want to like remove useless white space. Okay, and then the last rule we want to do is we want to be able to evaluate list files, and that returns a number as well. So, and there are like two things we do here now. First, we need to like get the parse content of the list file. So this will give us like a list of files. Yeah. I don't know, list. And what we ask here is parse the list file. And that gives us a list of strings. And then the next thing we do is we want to have like all the numbers that are in there. We get them by mapping over the list. And for each item in the list, we go and ask the build system, what is the value for parse dat of this item? And again, we need to tell it it's a number. And then in the end, we take all those numbers and reduce them, kind of like we fold over them, just using plus x plus y, starting from 0. Okay, so this is the specification of our whole build system. And as I said, like all those functions are very cheap, but in general, they're very expensive. And we want to avoid using them whenever we can. Okay. Any questions so far? And by the way, if you have any questions at any time, please interrupt me. Okay, I don't see any questions. Okay, so now we have used the API. Next step is to implement this API or something behind this API. And we need the graph file for this. All right, okay. So there are a few things already in here. So the first one we've already used is the graph reader, and the graph reader gives us a get value function or method. And the first argument we've put to this graph reader, or like to the get value function, was usually like one of those uppercase constants. And I call them like layers, kind of like your graph is layered, right? There's like the file system layer, then there's like the list parser layer and the data parser layer. And then on top, we have the evaluation layer. So I call them layer. And then, oh yeah, I've called the strings, which are file names in our case, key. So let's call them file here. And then we've also seen rules. And like a rule is something that takes a reader for the graph and the file string, and then computes a value using this data. So for instance, like this function is a rule, right? It takes a reader of the graph and a file and returns some data. And then the graph spec was just an object where for each layer we either gave a rule if it's like a node that needs to be computed, or null if it is meant to be an input node. Right. And then we have like, finally, we have the graph, which is the thing that we constructed. It takes a spec and gives us an object where we can ask, where we have get value, so it implements the graph reader interface. And we also have set input to set like values for like file contents. Okay, let's make this consistent. Right, okay, so we need to implement this. And this whole thing, like as I said, we want to do early cutoff. So there will be some notion of when has a file or like has a value been modified. So there's a notion of time. And to keep things simple, we just say type time is number. We just use numbers for time. And whenever we set a value, we just advance the time. And then we also need to store, we need to store all the nodes of our graph in this whole thing. So we need a notion of a node. And well, they're kind of like two things we want to store in a node, in every node. First, one of them is the value. And I said, like, we don't specify like the exact types for values. We just make it unknown. So you can store whatever you want, and you have to cast it when you get it out. And we also need to change, we also want to save at what time the node has changed the last time, because that determines if we need to rebuild something or not. And it will turn out later that for input layers, so this node type is enough. We don't need to store any additional data. But for rule layers, we want to store more data. So we distinguish like nodes for input layers look slightly different from nodes for rule layers. So there's something we need to fill in here, which I'll do later. Okay, and then for convenience, we also we need to store the layers we get in the spec. So they're like an input layer will pretty much just contain the nodes, which is a map from, so this string is meant to be a file name, and then we store a node. So for each input layer, we have one of those. And similarly, we want to have rule layers, which are similar. String, and then we have like a rule node. But we also need to store the actual rule for every rule layer, so we can actually do something. Okay, so with all these types, we can finally define all the fields we need in our class. So we need a notion of time. Let's call this time now. And we need to store all our input layers. And that is, again, that's a map from strings to an input layer. And this time the string, so maybe like it's good. String is a file. Here as well, string is a file. And here, the string is a layer name, or like a layer name. Right. In other languages, I would probably have used a map structure which is indexed by a pair, kind of like the layer and the file name, but that's almost impossible in JavaScript, at least in my understanding of JavaScript. And then we have rule layers, which are very similar. So we have a string and a rule layer. Again, the string is layer name. Okay, and now in our constructor, we need to initialize all of those, and we start simply with time 0. That's good enough. And then we walk over our spec. So for each layer mentioned in our spec, we check if the layer is an input layer. And how do we do that? We get the rule So just as a reminder, the spec type is like an object indexed by strings, and every value in there is either a rule or null. So if our rule is null, we have an input layer, and we just add this input layer to our list of input layers. So we say this input layers, and we set it at layer, and we just put an empty map in there. That's just convenient. So new map string input layer. Okay. Oh, and I forgot to initialize the input layer. So this input layers is new map string input layer. So we start out with an empty map. And here for the nodes, we actually want to put the nodes in there. So we need an empty map of nodes. Okay, cool. And similarly, we want to do it like for rule layers. We want to do something similar. So we say this rule layers, and we set at the layer, put the rule in, and the nodes are an empty map again. Rule node. No, I'm under the window, the Zoom window. Okay. So something is broken here. Oh, I mistyped. So many typos. Okay, cool. So now we have our constructor. Right. I guess not all of this makes perfect sense yet. It will, like, some parts will just become clear later, but are there any questions that are proper roadblockers right now? Okay, cool. So let's next get to set input. Oops. So what do we want to do? What do we need to do when we get a new input? We need to check if the layer we're given is actually an input layer, and if it is, we need to just set the value in there. So, and I have no intent to make this like really resilient, so I just assume we only get input layers. So, actually, no. So we want to get the nodes from the input layers, get layer, and we force it. Okay, so now we have like all the input nodes for this layer, and we might be setting, like, there might be three things might be happening. We might be setting a new input that has never been set before. We might be setting something that has already been set to a different value, or we might be setting something to exactly the same value. And whenever we set something to the same value, we want a shortcut, right? There's no point in recording this. If nothing has changed, we don't need to do anything. So let's distinguish those three cases. So first case, if the nodes don't have the file we are currently setting, that means we actually need to do something. And what we need to do is we advance the time, right? Like something has changed. So we say we increase the time. And then we say in the nodes, we add, for the file, we add something new. The value is the one we got, and change that as the current time. Right. Okay. So from now we can assume we already, like, somebody has already set a value for this file at this layer. So let's get the node. nodes get file. So, and then there's this shortcut case I mentioned, and that happens if the value we already have in the node is the same as the value we're supposed to set. And whenever we do that, we can just shortcut. And in the other cases, we need to, again, advance the time. And we need to change the node. So the node value is what? The new value. And the node changed at is now. This dot now. Okay. So that's all we need to do to set a value. Is there a question? Okay, obviously not. So implementing get value is more tricky than that. The idea is whenever we ask for a value, we need to update nodes across the whole graph. So what we're going to do is we're going to implement a helper function, which does pretty much all the work, and I'll call it update node. And it will get a layer as its input, and it will get a file as its input. And it returns the node at this layer, like the node at this address or node ID. So, well, suppress the warning. And then getting the value at a specific node pretty much just amounts to updating the node at this address and getting its value. Right. So let's walk through what we need to do when we need to update a node. So if we are asked to update an input node, we pretty much need to do nothing. We just need to return the node. So if input layers has this layer we're referring to, and let's do, it might be that this input layer has no node set at this for this file yet, or no value set for this file, right? This can happen, like you're referring to a file that does not exist, for instance. So we want to catch this case. So let's get the nodes at this layer. This input layer is get layer. And if the nodes do not have the file, then we throw an exception. Accessing unset value at, and then layer. Let's do it like this. That's consistent with what I did in other places. A layer file. Okay. And otherwise, if we do have the node, we just return, we just return nodes get file. Well, and we know the file exists because we've just asked for it value. No, just a node. Okay. So there's nothing we really need to update for input nodes. So if we made it here, we know we don't have an input layer, which means we have a rule layer. So let's get everything that's in the rule. So there's a rule, and there are nodes. This rule layers get layer, and we assume, we can make the conclusion that if it's not an input layer, it's a rule layer, and nothing bogus. Okay. So for rule layers, it might happen that it's the very first time we're trying to access a node in the graph. Nobody has ever tried to evaluate that file at that layer before, right? That happens, for instance, at a fresh build, like your whole graph is empty. So in this case, we need to compute the value and store it in the graph. So if not nodes as file, so if we don't have the file, we need to recompute it for the first time. And how do we do that? We say the value is the rule applied to, we need a graph reader. Well, this is a graph, and in particular a graph reader, hence at the file. That's how we compute the value for the new, for this node we just need to create. However, because we want to, like on rebuilds, we want to like minimize all the things we have to rebuild. So we need to implement some sort of dependency tracking, and kind of like get a hold of like, what does calling this route in this graph at this file, like what other calls to get value does it make? And in a language where you have higher order functions, you can just intercept all those calls. And that is something we're going to implement next as a helper function. So we want something private function, and I call it get traced reader. And what it returns is a database, not a database, a graph reader. But it also returns a trace. And the trace is a list of node IDs. And we need to define what a node ID is. A node ID is just the address of a node in this whole thing. So that's the layer and the file node ID. That's how we can address a node in the graph. So we return a list of node IDs. How do we do this? Okay, we need to build up a closure. So we need an empty, we start with an empty trace. And now we also need to add a function that we put in the graph reader we return. So we want a get value function, and get value takes as input a layer and a file, and return something unknown. And the only thing we do when we call get value in this one, first of all, we add like what we're trying to get to the trace. So we say trace push layer file. And then we simply call kind of like ourselves with the layer and the file. And we want to return. No? And we want this. Okay, so to some extent, and then in the end we return both. So we return get value and trace. So the object you get returned from get traced reader behaves exactly the same as the class instance we currently have. But in addition to that, it also tells you all the calls to get value that have happened. So yeah, it's tracing the calls to get value. So, and our plan is to use this whenever we apply the rule to track the dependencies. So what we need to do as well for rule nodes, I said we need to add a bit more. And one thing we want to add are the dependencies we've tracked. They will become interesting later. And we also, in order to be able to do early cutoff, we also need to store at what time we've last updated this node. This will come apparent a bit later why, but I think it makes sense to add it now. Right. Okay, so let's, instead of calling rule with this, we want to use a trace reader here. So let's get a reader. Oh no, wait, let's get a reader using this get trace reader. And then we use the reader instead of this. And now we create a new node. And we have a rule node. And the node will contain a value. Well, that's the value we just computed. It will have a time when it was last changed. That is now. It will have dependencies, and the dependencies are exactly what the reader has traced, like the trace reader has traced for us. Those are all the dependency trace. And then we have this timestamp for updated at, and that's now because we've just changed this, or like we've updated the node. Okay, and we need to add this whole thing into the nodes of this layer. So nodes set file node, and we need to return the node. So that's the case of adding a fresh node. Cool. So now we know we're in a situation where the node has already been evaluated before. So it's not the first time. And we want to do a few things to do early cutoffs. The most, I guess the most obvious one is like checking if the dependencies have changed or not. If the dependencies have not changed, we know the value cannot have changed. Well, I'm working under the assumption that all our rules are pure. Maybe I should have said that earlier. But I think that's how build systems work. So I think that's like a very obvious cutoff. There's another cutoff, like we might run into the same nodes multiple times during one build. And there's pretty much no point in doing anything after the first time. That is what this updated at is for. Like it tracks the last time we call node update, update node, updated add. So the shortcut we want to add is if the node, oh wait, first of all, we need to get the current node. So node is nodes get file. So if the node has been updated at time now, that means we already know it's up to date and we don't need to do anything. So we can just return the node and be done. And the next thing is dependency checking the dependencies. So what we want to find out is have the dependencies changed, and that's a Boolean. And for now, we assume they have not changed, and then we run over all the dependencies and check. So for dep in now off. So for all the dependencies of the node, we check if we update the dependency node. This update node at dep.file. And if we find out the last time it has changed was after we looked the last time at the current node. So if the dependency has changed after we've updated this node the last time, that means like the dependency has changed, right? And like one of the dependencies is done, is out of date. So no, not now. I mean node updated at. And if that is the case, we say dependencies changed is true, and we can stop looking through the dependencies. What is wrong here? Oh, okay. So that is early cutoff. Okay, so now if the dependencies have not changed, we know the value has not changed and we can just return. But before we return, we want to say we want to record that we've actually just updated the node. So this node is up to date, right? We know its value is up to date because none of its dependencies have changed. So we say we have just updated it now, and then we can return the node. Cool. Okay. So next thing we know is one of the dependencies have changed, and that means we need to reevaluate the node. And we do that pretty much the same way we do it up here. We construct a new reader, a trace reader, and then get the value. And now there's another thing we can optimize. It might, like sometimes it happens that the inputs have changed, but the value has not changed, right? For instance, like in our addition thing, I don't know, like before your inputs were 3 and 5 and the sum is 8, now they're 4 and 4 and the sum is still 8. So kind of like you don't need to update the time at which you've changed, because like your consumers, for your consumers, it looks like nothing has happened. So that means we only need to update when we have changed the last time, if we have actually changed. So no value, if that value is not the same as the new value we've just computed, then we say the value is the new value, and we also say we've just changed now. Okay, and regardless of whether we have changed or not, we need to update our dependencies, right? Like our dependencies could have changed without our value actually changing. I don't know, for instance, we could have replaced one file containing 5 by another file containing 5. But for the sake of like future dependency checks, we want to look at the new dependencies, not at the old dependencies. So we say node dependencies is the trace we get from the reader. And then we want to also say that we've just called update this.now. And once we have that done, we can return the node. Okay, that's it. That's the whole implementation. Let's see it in action. So let's open a terminal, right? And let's call yarn demo, and demo will call the thing we've described up here. So what we expect is 55, 37, 37. Let's see if that happens. I guess we crash. No, we didn't. Okay, cool. So that means all the reevaluations have happened in the way we intended. I guess what we can't really see here is like what computations have actually happened, right? I could just like reevaluate everything all the time and you wouldn't see. So to convince you that we're doing the right thing, let's add a bit more logs. So let's log here that we've updated. We've called parse list on file. And here we've called parse dot on file. Here we've called we've called eval list on file. Okay, now we have a lot more things to see. And let's run it. Okay, and there's this annoying to do, which makes no sense anymore. Cool. So first run, what we're doing is we're calling parse list on the main list, and we're calling parse dot on both files, and then we call evaluate. Well, we need to touch everything because it's a fresh build, so that's fine. Next, what happens next is we've changed the value of bar.dat to 24. And we ask again, what's the value? And we see we only parse that, like we only pass bar.dat and then evaluate. We don't parse the old file anymore. We don't parse food.dat and we don't parse the list. So that's cool. Next, we change the value of bar.dat to 24 with a few spaces around. And we see the only function we call is parse.dat. And then we see, oh, the value is the same, so we can stop. And we know all other nodes are up to date. And maybe one last thing is, if we don't do anything and just call again, we expect to print 37 and no more outputs. See if that works. Yes, 37 again, and no calls to functions in the middle. Okay, cool. That is a monadic build system implemented in 139 lines of TypeScript.